Hello everyone, and welcome to today's presentation. I'm excited to share with you insights on thickening in water resource recovery facilities. This is the first slide, which serves as our cover. We'll be exploring how thickening plays a vital role in managing sludge more efficiently, cutting costs, and optimizing operations. Over the next few slides, we'll cover the process itself, its benefits, and its impact on overall facility performance. So let's get started. Let's talk about why thickening really matters in our processes. First, when we increase the solids content in sludge from 2% to 8%, we can reduce the overall sludge volume by about 75%. This is a huge difference, and it translates directly into lower operational costs. You'll see savings across many parts of the facility, including heating, pumping, and chemical treatment systems. Now, on the process efficiency side, thickening helps us by reducing the water content before downstream steps like anaerobic digestion. With less water to handle, we need smaller equipment and less energy to operate it. This not only makes our facilities more sustainable, but also more cost-effective in the long run. So overall, thickening is a key step that impacts both costs and efficiency, helping us optimize our operations while supporting our sustainability goals. Now, let's take a closer look at the different thickening technologies available and how they fit into the overall sludge management process. First up, we have gravity thickeners. These rely on a simple physical settling process, and they can typically achieve total solids concentrations of about 2 to 15%. They're particularly effective for primary sludge and lime-conditioned solids. One of the key advantages here is their straightforward operation and lower cost, though they do require a larger footprint compared to some other options. Next, we have dissolved air flotation, or DAF. This technology uses tiny air bubbles to float solids to the surface, reaching about 3.5 to 8% total solids. It's especially good for waste-activated sludge and aerobically digested solids because of its excellent capture rates. The ability to separate solids efficiently makes it a popular choice in many treatment plants. Moving on, there's the gravity belt thickener. This process uses a polymer conditioning step, and the sludge drains through a porous belt, achieving total solids levels between 4 and 10%. It's known for its compact design, making it suitable for space-constrained facilities, and it offers high reliability with capture rates exceeding 95%. Then we have rotary drum thickeners. These feature a rotating perforated drum with internal flights, which helps concentrate solids to about 5 to 12% total solids. They are quite space-efficient and are ideal for waste-activated sludge, especially when lower energy consumption is a priority. Finally, let's look at centrifuges. These units spin at high speeds, creating forces between 500 and 3000 G, which allows them to achieve total solids concentrations of 3 to 15%. They are versatile, capable of handling all types of sludge, and have the smallest footprint among these options. However, they do come with higher energy requirements. In summary, understanding these different thickening options helps us choose the right technology based on space, cost, energy use, and the specific sludge characteristics we're dealing with, an essential part of designing an efficient and effective treatment process. Gravity thickeners are actually one of the oldest and simplest technologies we use for thickening sludge. They come in circular or rectangular shapes and work similarly to clarifiers. Essentially, solids naturally settle to the bottom of these tanks, while the clearer water, or supernatant, flows over weirs at the top. Now, how do they operate? Sludge enters through a central feed well, which is designed to distribute the flow evenly and reduce turbulence. This even distribution is key to efficient settling. Inside the tank, solids settle by gravity onto a sloped floor, typically with a pitch between 2 to 3 to 12. As the sludge collects, slow-moving scrapers or plows gently push it toward a central hopper. From there, the sludge is pumped out for further treatment. An important feature is the collector mechanism, which has pickets that gently agitate the sludge blanket. This helps release any trapped gas bubbles, which could otherwise cause bulking and disrupt the process. For primary sludge, the thickening typically results in a solids concentration of about 5 to 10% total solids. When we combine primary and secondary sludge, the concentration tends to be lower, but still effective for our purposes. Let's touch on some key design parameters. These tanks usually have a depth of about 3 to 4 meters, or around 10 to 13 feet. The diameter can be quite large, up to 25 meters, about 82 feet, especially for bigger plants. The detention time, which is how long the sludge stays in the thickener, generally ranges from 24 to 48 hours for primary sludge. In terms of loading, solids loading is typically between 100 and 150 kilograms per square meter per day for primary sludge, and hydraulic loading ranges from 15.5 to 31 cubic meters per square meter per day. All these parameters help ensure the thickener operates efficiently, producing a sludge that's thick enough for downstream processes, while maintaining stable and reliable operation. Let's take a closer look at the factors that influence the performance of gravity thickeners. First, sludge characteristics are really important. Fresh primary sludge tends to thicken more effectively than aged or combined sludges. The key here is the nature and freshness of the solids, which significantly impact how quickly they settle and the final concentration we can achieve. Next, temperature effects play a crucial role. When temperatures are higher, there's a greater risk of septic conditions and odors developing. On the other hand, lower temperatures increase water viscosity, which slows down the settling velocities and means we need longer detention times to get the desired thickening. Now let's talk about loading rates. It's critical to maintain the design solids and hydraulic loading rates. Overloading the system can lead to rapid sludge buildup, potential septic conditions, and carryover of solids into the supernatant, which we definitely want to avoid. Finally, process control is key. Consistent, continuous feeding helps us achieve optimal results. Sometimes, using dilution water can be beneficial. It helps control detention time and prevent septicity, especially when working with combined sludges. All these factors are interconnected and essential for maximizing the efficiency and effectiveness of our gravity thickeners. Now let's look at how dissolved air flotation thickeners, or DAFTs, operate. Essentially, they use compressed air to change the specific gravity of solids, making them float to the surface. The process begins by dissolving air into recycled water under pressure, typically between 40 and 80 psi, in a saturation tank. When this pressurized mixture enters the DAFT at atmospheric pressure, tiny bubbles, less than 100 micrometers in size, are released and attach themselves to the solid's particles. This attachment causes the solids to become buoyant and float to the surface, forming a layer that's usually about 200 to 610 millimeters deep. That float layer is then skimmed off the top. Meanwhile, the heavier solids settle to the bottom and are removed as underflow. Both of these streams are collected and removed by conveyors. Looking at performance characteristics, the float solids typically contain about 3.5 to 4% total solids, while the underflow solids range from 3 to 8%. The recycle rate can be quite high, between 100 and 200% of the influent flow, which helps maintain efficiency. Without using polymers, the capture rate of solids is around 95%, which is quite effective. DAFTs are particularly well suited for thickening waste-activated sludge and aerobically digested solids. They excel at handling biological sludges with very fine particles that don't settle easily through gravity alone. And of course, the process can be enhanced further by adding polymers, which increase the loading rates and improve overall performance. So, in the context of our overall treatment process, DAFTs offer a reliable, efficient method for thickening biological sludge, especially when dealing with fine particles that are challenging to settle naturally. Now, let's look at how the DAFT operation and control work. First, air saturation occurs in the saturation tank, where compressed air dissolves into the recirculation water at pressures between 40 and 80 psi. Achieving the right pressure is crucial because it creates optimal bubble sizes, which are essential for effective flotation. Next is bubble formation. When this pressurized water enters the atmospheric part of the DAFT, the pressure drops and tiny bubbles form. The size of these bubbles, ideally around 50 micrometers, is a key factor because it influences how well solids can attach and be floated. Moving on to solids flotation, these tiny bubbles attach themselves to solids particles, reducing their overall density below 1. This causes the particles to rise to the surface, forming a float that can easily be removed. Then we come to collection. The float at the surface is removed by top skimmers, while bottom scrapers collect any settled solids. The clearer water, or subnatant, is then returned to the headworks of the facility for further treatment or reuse. Finally, there's a simple rise rate test using a 1-liter graduated cylinder. This test helps us monitor how well the DAFT is performing. Normally, rise times should be between 10 and 25 seconds. If the rise is slow, it might indicate issues like low polymer dosage, an improper air-to-solids ratio, or overloading the system. Keeping these parameters in check ensures optimal operation and treatment efficiency. Gravity belt thickeners, or GBTs, are a real game changer in thickening technology. They are designed to be compact yet highly efficient, making them ideal for space-constrained setups. These units work by removing free water from polymer-conditioned sludge as it moves across a porous, moving belt, which is quite innovative. Now, let's walk through the process flow. First, polymer is injected into the sludge feed line through a high-energy mixing zone, usually using an inline variable orifice mixer. This ensures thorough mixing and proper conditioning of the sludge. Next, the conditioned sludge flows into a flocculation tank, where it stays for about a minute. This detention time allows for proper flock formation, which is critical for effective thickening. From there, the sludge overflows onto the moving belt. As it travels, chicanes or plows gently turn the sludge, encouraging trapped water to drain through the clear sections of the porous belt. At the discharge end, there's an adjustable ramp that provides extra dewatering time, making the process even more efficient. Looking at the key components, you'll notice the flocculation tank with a slow-speed mixer, which helps with flock formation. The porous woven polyester belt is central to the process, allowing water to drain through it. Chicanes facilitate gentle agitation, preventing sludge breakup. The belt drive is variable in speed, typically between 5 and 20 RPM, giving us control over the process. Additionally, there's an adjustable discharge ramp for enhanced dewatering, and a high-pressure wash system operating between 585 and 620 kPa to keep the belt clean. A doctor blade ensures the belt stays free of buildup, and progressive cavity discharge pumps help move the thickened sludge efficiently out of the system. Together, these features make GBTs a compact, high-performance solution for sludge thickening, perfectly aligning with our overall goal of optimizing treatment efficiency while saving space. Let's take a closer look at GBT performance and the control variables that influence it. First, polymer conditioning is absolutely critical. The type of polymer you choose and the dosage you apply can make a big difference. For example, doses typically range from about 1.5 grams per kilogram, which is roughly 3 pounds per dry ton, for raw primary sludge, up to 6 grams per kilogram, or around 12 pounds per dry ton, for sludge that has been anaerobically digested. To determine the best polymer type and dosage, proper jar testing is essential. This helps us find the optimal conditions for effective flocculation. Next, let's talk about mixing energy. The inline mixer creates turbulence that disperses the polymer evenly throughout the sludge. The key here is adjusting the orifice opening to control the mixing intensity. If the mixing is too gentle, we risk poor flock formation. If it's too aggressive, we might shear the polymer chains, reducing their effectiveness. Balancing this is crucial for optimal results. Moving on to belt speed, slower speeds increase the retention time, which allows for better thickening of the solids. They also help concentrate the solids more effectively. But if we speed up the belt, we increase throughput, which is good for productivity. However, faster speeds can sometimes reduce the dryness of the final cake, so operators need to find that sweet spot, balancing speed with feed rate to achieve the best performance. Finally, hydraulic loading varies depending on the belt width. For instance, A 1-meter belt typically handles between 100 to 250 gallons per minute, while a 3-meter belt can handle 300 to 750 gallons per minute. Also, the feed solids concentration influences how much polymer is needed. The thinner the feed, the more polymer you generally require to achieve proper flocculation and thickening. All these variables, polymer conditioning, mixing energy, belt speed, and hydraulic loading, are interconnected. Managing them carefully helps us optimize the GBT process, ensuring efficient operation and high-quality outputs. Let's talk about the GBT solids loading and capture rates. When it comes to loading, we typically see a minimum of around a few kilograms per meter per hour, and the maximum can go quite a bit higher depending on the operation. Now, what's really impressive is that GBTs consistently achieve solids capture rates of over 95% when they are properly operated. That's a key point because it highlights the efficiency of this technology. The concentration of thickened sludge usually falls between 4% and 10% total solids, or TS. Meanwhile, the feed solids, meaning the solids going into the system, range from about 0.4% up to 8% TS. This variation is important because it affects how well the system performs. Performance, of course, depends on several factors. The characteristics of the sludge itself play a role, as does the effectiveness of the polymers used. Plus, operational adjustments, things like belt speed, ramp angle, and mixing energy, are critical for optimizing the process. Connecting this to our overall theme, understanding these loading and capture rates helps us optimize systems for maximum efficiency, ensuring we meet our treatment goals effectively and reliably. Let's take a closer look at the rotary drum thickeners and their compact design. These units are a great space-saving option for sludge thickening, especially when dealing with waste-activated sludge, or WAS. The key feature here is the rotating perforated drum, which typically spins between 5 and 20 revolutions per minute. Inside, you'll find internal flights or screw conveyors that work to move the conditioned sludge along the length of the drum. Now, how does it operate? Well, polymer-conditioned sludge is fed into a flocculation tank just before reaching the drum. The rotating drum then lifts the sludge up along its sides. When the sludge reaches the top, it falls back down, and during this process, free water is able to drain through the perforations into a collection trough beneath. Meanwhile, the internal flights are constantly pushing the sludge towards the discharge end, ensuring continuous movement. Looking at performance specs, these units can handle feed capacities of up to 180 cubic meters per day for larger models. They typically produce a thickened solids concentration ranging from 5 to 12% total solids, and for WAS, the feed concentration is usually between 0.5 and 1% TS. The capture rate is quite high, between 93 and 99%, meaning most of the solids are retained. The polymer dose varies from 2 to 7 grams per kilogram, depending on the sludge type, and the drums are made from durable materials like stainless steel wedgeware, perforated plates, or polyester fabric. So why are rotary drum thickeners attractive? They have a small footprint, which makes them ideal for limited space. Their enclosed design helps control odors, and they generally consume less energy compared to centrifuges. Plus, they are relatively simple to operate, making them suitable for small to medium-sized facilities. Overall, they are a practical, efficient option for sludge thickening needs. Now, let's talk about centrifuge thickening and the maximum force it can generate. Centrifuges use rotational acceleration to create incredibly high forces, ranging from 500 to 3,000 times Earth's gravity. This intense force dramatically speeds up the separation process, allowing solids to be separated from water very efficiently. Typically, these machines operate at speeds between 1,000 and 3,000 RPM, which enables them to thicken all types of sludge to concentrations between 3 and 15% total solids. Next, let's look at how the feed enters the centrifuge. Conditioned sludge is introduced through a stationary feed tube into the center of a rotating bowl via an inlet distributor. This setup ensures a smooth and controlled entry, setting the stage for effective separation. Once inside, The high-speed rotation causes the denser solids to be pushed outward toward the bowl wall, while the lighter water remains closer to the center. This centrifugal force creates a rapid and clear separation of solids from water. Moving on to solids conveyance, there's a scroll conveyor inside the bowl. It rotates slightly slower than the bowl itself and scrapes or conveys the solids from the wall toward the discharge end, which is conical in shape. This movement ensures the solids are effectively moved out of the separation zone. Finally, the clarified water flows over adjustable weirs at the opposite end of the centrifuge. By adjusting the weir height, we can control the pond depth and, consequently, the amount of water discharged. This entire process highlights how centrifuges efficiently separate solids from water, contributing to effective sludge management. Let's take a closer look at the centrifuge process variables that are crucial for optimal operation. First up is bowl speed. This is set during commissioning, and it determines the G-force applied during separation. Higher speeds generate more force, which can enhance solid separation, but it may also reduce the dryness of the resulting cake. Typically, we're looking at speeds between 2,000 and 3,000 RPM, which produce G-forces ranging from about 500 to 3,000. Next, we have differential speed, which is the difference in RPM between the bowl and the scroll. This setting controls how long solids stay in the centrifuge. Longer retention times usually mean a drier cake, so lower differential speeds, say between 1 and 20 RPM, give us that longer retention. Conversely, higher differential speeds make the solids discharge faster, which results in a wetter cake but can improve throughput. Then there's pond depth, which is managed through the weir height. Pond depth influences the size of the clarification zone and the quality of the centrate. A deeper pond generally helps improve the clarity of the centrate, but it can also lead to a wetter cake, so there's a balance to strike here. Moving on to the target thickened solids, we usually aim for about 5 to 6% concentration. This level ensures we maintain pumpability for downstream processes, which is critical for smooth operation. For centrate quality, the maximum suspended solids we're aiming for is around 500 milligrams per liter. Keeping within this range ensures the centrate is acceptable when returned to the headworks, preventing downstream issues. Finally, the polymer dose range typically falls between 4 to 8 grams per kilogram of dry solids, or roughly 8 to 16 pounds per dry ton. Proper polymer dosing is essential for effective conditioning of digested solids, helping improve dewatering and overall process efficiency. Understanding and controlling these variables helps us optimize the centrifuge's performance, ensuring we achieve the right balance between dryness, clarity, and throughput, key factors for the success of the entire process. Polymers are actually key conditioning chemicals that play a crucial role in improving both thickening and dewatering processes. They do this by making solids particles coagulate and form larger, more manageable flocks. These large molecules, which have high molecular weights, act as both coagulants, which destabilize colloidal suspensions, and flocculants, which bridge particles together into bigger masses that are easier to separate from water. Now, why do polymers work so well? Well, wastewater sludge particles, especially in waste-activated sludge, carry negative electrical charges. These charges cause the particles to repel each other, keeping them suspended and stable. Cationic or positively charged, polymers come into play here. They neutralize these negative charges, allowing the particles to come closer together. Once neutralized, the long polymer chains can bridge between particles, helping form large flocks that settle or separate more easily from the water. It's important to note that primary sludge has weaker negative charges and tends to settle more readily, so it often requires less or no polymer. In contrast, waste-activated sludge has stronger negative charges and smaller particles, making the use of polymers essential for effective thickening and dewatering. Let's also talk about some key characteristics of polymers. They can carry different charges, cationic, anionic, or non-ionic, depending on their application. The charge density indicates how many charged sites are along the polymer chain, which affects how well it interacts with sludge particles. Molecular weight refers to the length and complexity of the polymer chains, influencing their bridging ability. Polymers come in various forms: dry powders with over 90% active content, emulsions with 25 to 50%, or liquid solutions. For waste-activated sludge, high-charge density cationic polymers tend to be the most effective. And of course, selecting the right polymer involves jar testing. This is where we match the polymer characteristics with the specific properties of the sludge to ensure optimal performance. Let's take a closer look at dry polymer systems. First, we have the dry polymer feed. This involves volumetric feeders such as screws, augers, vibrating units, or discs that sprinkle individual polymer grains into the wetting zone at carefully controlled rates. Proper calibration here is crucial because it ensures accurate dosing, which is essential for maintaining consistent polymer performance. Next is the initial wetting stage. This is a critical step because each particle must be fully wetted to prevent issues downstream. Washed on water creates a smooth flow over the funnel surfaces, immediately transporting these particles into the mixing zone. Ensuring thorough wetting at this stage helps avoid problems later on. Then we move into high-energy mixing. Eductors use water pressure, typically between 200 and 400 kilopascals, to generate a high-velocity flow. They leverage the Venturi effect, providing intense mixing that saturates the polymer particles and begins the process of uncoiling the polymer chains. This step is vital for activating the polymer effectively. Following that, we have the aging tank. Here, the mixture is gently mechanically stirred at speeds up to 500 RPM for anywhere from 30 minutes to 2 hours. This allows complete polymer activation, and proper aging ensures that the polymer is fully ready for use, maximizing its effectiveness in the process. After aging, the activated polymer is diluted to a target concentration, typically around 0.25 to 0.5%. This diluted solution is then fed into the thickening process. We often use day tanks to store the polymer solution for up to 24 hours, providing flexibility in operations. Finally, I want to highlight a common issue called fish eyes. If the dry polymer isn't properly wetted, it can form gelatinous balls that float on the solution surface. These are called fish eyes. Once formed, they can't be corrected, meaning the entire batch must be disposed of and the equipment thoroughly cleaned. This underscores the importance of proper wetting and mixing to avoid costly rework and downtime. Understanding these steps and their significance helps us ensure the polymer system operates smoothly and efficiently, which is key to the overall success of our process. Let's take a closer look at emulsion polymer systems and how they work. These systems inject neat polymer, typically between 25 and 50% active content, into a high-velocity water stream. The energy from mixing then breaks the emulsion and starts the process of polymer activation. This setup can feed directly into the process or include aging tanks, also known as day tanks, which provide additional time for activation and operational flexibility. Now, the critical equipment involved includes a storage tank for the neat polymer, which should have gentle mixing to keep the polymer uniform. We also need a precision metering pump to control the polymer flow accurately, and a polymer injection point equipped with a check valve to prevent backflow. For mixing, a high-energy chamber or eductor is used to ensure effective dispersion, and sometimes, an optional mechanical mixer provides extra energy if needed. The system also requires a dilution water supply, typically under 200 to 400 kilopascals of pressure, and a day tank to store the activated solution for later use. One major advantage of emulsion polymers over dry systems is that they are much easier to make up properly. This reduces the risk of wasting batches and eliminates dust hazards during handling. The liquid form also avoids issues related to moisture exposure during storage. Although emulsion polymers tend to be more expensive per pound than dry powders, the higher success rate in proper makeup often makes them more cost-effective overall. Finally, maintenance is an important focus here. The check valve at the injection point needs regular cleaning because when polymer and water meet in the valve, sticky gel can form. Over time, this sticky buildup can prevent proper sealing and cause system plugging. To avoid downtime, it's best to establish a proactive cleaning schedule and keep spare valves on hand. In summary, emulsion polymer systems offer a flexible, easier-to-handle alternative to dry powders, but they do require attentive maintenance of key components like the check valve. Understanding these aspects helps us optimize performance and minimize operational issues. Now, let's take a closer look at polymer dosing and performance. As you can see, the amount of polymer needed can vary quite a bit depending on the type of sludge and the treatment process involved. For raw primary sludge, the polymer dose is relatively minimal, around 1.5 to 2 grams per kilogram, or about 3 to 4 pounds per dry ton, because this sludge contains larger, heavier particles that have weaker charges. In contrast, waste-activated sludge, or WAS, requires a higher dose, roughly 3 to 4 grams per kilogram, since it consists of smaller particles with stronger negative charges, making them a bit more challenging to separate. Digested sludges demand the highest polymer doses, typically between 5 and 7 grams per kilogram, or 10 to 14 pounds per dry ton. That's because biological treatment breaks down the particles into even finer materials, which are more difficult to separate effectively. One key point I want to emphasize is the importance of regular jar testing. These tests are vital for optimizing both polymer selection and dosing. Since sludge characteristics can change due to seasons, influent variations, and process modifications, it's crucial to test consistently. Ideally, testing should be done weekly or whenever you notice performance issues. This approach helps ensure you're using the most cost-effective polymer while still achieving target capture rates above 95%. Ultimately, maintaining proper dosing not only improves treatment efficiency, but also helps control operational costs. Let's discuss process control and optimization, starting with hydraulic loading rate. It's crucial to monitor flow rates continuously to make sure they stay within the design parameters. We calculate the hydraulic loading rate, or HLR, by dividing the flow by the surface area. If the HLR exceeds the designed limit, it can lead to poor solids separation and solids carryover in the filtrate or centrate, which we definitely want to avoid. Next is solids loading rate. This measures the mass of dry solids per unit area per unit time. Interestingly, SLR often limits throughput more than HLR does. To calculate it, we multiply the flow rate by the solid's concentration and then divide by the surface area. Keeping an eye on SLR helps us prevent overloading the system. Moving on to capture rate analysis. This tells us what percentage of influent solids are actually being captured in the thickened sludge. Our target is over 95% capture. If the capture rate drops, it can indicate issues like polymer problems, overloading, or mechanical failures, all of which need immediate attention to keep our process running smoothly. Finally, performance trending is essential. We track variables like polymer usage, solids concentration, and capture rates over time. If we notice a gradual increase in polymer demand, it might point to changes in sludge characteristics or equipment wear. Recognizing these trends early allows us to make necessary adjustments or maintenance before more serious problems develop. All these controls are interconnected and are vital for optimizing our process efficiency and ensuring quality outcomes. Let's talk about some safety and operational best practices that are crucial for our success and safety. First, safety considerations. Slip and fall prevention is key because polymer surfaces can become extremely slippery. Always use absorbent granular powders, not water, to clean spills, and keep walkways clean and dry to prevent accidents. When it comes to lockout and tagout procedures, it's essential to follow the proper steps before doing maintenance on rotating equipment. Never bypass safety interlocks. That's a critical safeguard. For confined space entry, like when working in thickener tanks, proper atmospheric testing is a must because gases like hydrogen sulfide can be present. Always adhere to strict entry procedures to keep everyone safe. Personal protective equipment is your frontline defense. Wear respiratory protection when handling dry polymers, and use gloves and eye protection around all polymer systems to prevent exposure. When working around moving equipment, Make sure loose clothing, jewelry, and hair are secured away from rotating machinery, and ensure all guards are in place during operation. Now, moving into operational excellence. Regular monitoring is vital. Check your equipment at least once per shift. This includes pumps, mixers, collectors, and wash systems to ensure everything is running smoothly. Preventive maintenance is equally important. Follow the manufacturer's schedules for lubrication, belt replacement, bearing inspections, and replacing worn parts to avoid unexpected breakdowns. Keeping detailed records is essential for tracking performance. Document influent and effluent flows, solids concentrations, polymer usage, and equipment readings. This helps us identify trends and optimize our processes over time. Jar testing is a key part of ensuring our polymer dosing is effective. Conduct these tests regularly and don't rely solely on supplier recommendations. Verify performance with your specific sludge. Lastly, odor control shouldn't be overlooked. Maintaining proper ventilation in thickening areas is necessary, and using dilution water in gravity thickeners can help prevent septic conditions. By following these best practices, we not only ensure safety, but also optimize our operations for better efficiency and compliance. Thickening is really the foundation for effective solids management in water resource recovery facilities. It acts as a critical bridge between the initial liquid treatment steps and the final solids processing. By reducing the sludge volume by anywhere from 50 to 75% before it moves on, thickening not only cuts down on operational costs, but also helps improve the overall performance of the facility. When it comes to choosing the right thickening technology, it's important to consider factors like the type of sludge you're dealing with, the space available, how complex you're willing to handle operations, and your budget. For example, gravity thickeners are great for primary sludge because they're simple to operate. If you're working with waste-activated sludge, technologies like gravity belt thickeners or rotary drums can offer compact and reliable performance. And if you need maximum flexibility with a small footprint, centrifuges are often the best choice. Polymer optimization is another key point. Selecting the right polymer and dosing it correctly can significantly influence your operational costs and the effectiveness of the process. Regular jar testing, proper system maintenance, and ensuring the makeup water quality are all essential practices. When done well, they can help you achieve capture rates of over 95%, which is a real game changer for efficiency. Process integration is also vital. The way thickening fits into the entire solids train affects multiple parts of your facility. For instance, the filtrate or centrate that returns to the headworks can increase the load on your plant by 3 to 6%. Plus, the concentration of the thickened solids influences digester sizing, heating costs, and how well you can dewater the sludge later. So it's all about optimizing the entire process chain together. Lastly, continuous improvement is key. Regularly monitoring performance trends, inspecting equipment, keeping detailed records, and staying informed about new technologies all help you refine your operations. Even small improvements in thickening efficiency can lead to significant cost savings and environmental benefits over time. Remember, effective thickening really comes down to understanding the science of solids-water separation, choosing the right technology, maintaining your equipment properly, and always looking for ways to optimize through data analysis and testing. Master these fundamentals, and you'll build a solid foundation for successful solids management across your facility.